Okay, so let me continue our discussion about the insertion sort. But for this part, I want to give you the conclusion first. We say insertion sort running time is O n squared. Okay, so what is big O? Well, usually we read that as big O, but for some professors, if they read them as other and instead of big O, and you should understand that. Okay, so when we are saying an algorithm is big O n squared, what does that mean? Or we say it is big O and then parentheses with a function or a polynomial of O. What does that mean? And this means if we say a function is fn is a OGN, and this means that there should be a constant c and a constant n0, where if fn is smaller or equal to c multiplied by gn for all the positive values when n is greater than n0. Okay, and if you want to do this formal definition, and this means fn and then it exists, so this exists a positive constant c and 0 such that fn is smaller than c multiplied by gn, and this is for any, so for any n greater than n0. Okay, so this is the formal definition of the big O, but it may still look confusing, right? So no worries. So remember, just in the last video we talked about Tn, and what is Tn? Tn is the total cost of how much time or what is the effort of executing an algorithm if the input size is n. So ideally, Tn should be a polynomial of n. Okay, so and then if we have the Tn, and then we just write it as a n squared plus bn and plus c. Okay, so this is the polynomial. And then, let's try to find a c and a n0 so that we can figure out a gn. So this is the math trick I'm going to do. So for this part, a n squared, I'm going to a n squared is guaranteed to be smaller than a plus b plus c n squared, right? Let's assume that b and c, they're all positive. So a is smaller than a plus b plus c. So a n squared is smaller than a plus b plus c n squared. So the first term. And the second term, bn. bn is guaranteed to be smaller than a plus b plus c n. Okay, so the second term is guaranteed to be smaller or equal to this term, and then the last term, the same thing, c is guaranteed to be smaller than a plus b plus c. Okay, so now we have a plus b plus c in all three of the terms, and then let's put them together, and then, this term is small, this part is guaranteed to be smaller than 3 a plus b plus c n squared. Okay, so what are we doing? We are getting rid of the lower polynomial terms, and we are saying a n squared plus bn plus c is smaller than 3 a plus 3 a multiplied by a plus b plus c and then n squared for all the n greater or equal to 1. Okay, so why this is important? So remember, when we are figuring out the big O, there are two important constants we have to figure out. The constant c and then the constant n0. Okay, let's come back. So for this part, for the c, we can use that as the 3a plus b plus c. So that is the constant c. And then for the constant n0, we can use that as n greater n0 equals 1. So what do we have? So this part, 3a plus b plus c, that is a constant c. And then for that for that 1, that is n0. So what do we have? So for this polynomial, it is guaranteed to be smaller than c n squared for all the positive values n when n is greater than n0 and n0 is 1. So after having that, what can we say? We can say this polynomial is O n squared, right? Okay, so this is how we figure out whether such a polynomial is an O n squared or not. But our work is not done yet. So is insertion sort O in cube? Think about that. Well, and to your surprise, it is actually true. Okay, so how come? Okay, so well, we are doing one more step. So for this part, if we stop here, and then we can say for this term, it is guaranteed to be smaller or equal to this part. Okay, so let me come back. So we stop here originally, but if we want to slack it even further, or we want to increase it even further, well, n squared is guaranteed to be smaller or equal to n cubed for n greater than 1, right? Okay, so in this case, well, this means, well, instead of saying it is O n squared, we still have the same polynomial c. We still have the same constant c. We still have the same constant n0. However, now we have n cubed instead of n squared. So the question is the insertion sort O n cubed? The answer is yes. Because, well, the rule is if we want to increase it to a higher degree of polynomial, we can still make it. Okay? But, okay, so let's answer. Let me revert back. I don't want to mess it up. Okay, and then how about, so for this part, it is true. And for this part, is that true? The answer is no. We cannot say, well, if we get rid of this n squared and we only say n, so this math doesn't work this way. So if we want to increase the degree of polynomial to n to 4 or n to 10, we can use the same trick. However, if we want to decrease the degree of polynomials, we can't do that. So for the first part, it is true, and for the second part, it is false. Okay, and and for the big O, suppose that you have a Fn, and the Fn is not just a 2-degree polynomial, it can be k-degree polynomial, so it can be super long. So if you have a polynomial bk n to k, and then bk minus 1, and n to k minus 1, and then all the way down to a b1n and b0. Okay, and then if we want to do the same trick as we have done here, and eventually we can put all the sum of the bk minus 1, bk minus 2, and all the way to b1, b0. We put them together, and eventually you will get something like this. So, well, this Fn is guaranteed to be smaller or equal to Cn to the k. So this top polynomial is O n to the k, and the process is exactly the same. Okay, so well, this is for the upper bound. So this is for the big O, because we are trying to do what? We are trying to find a upper bound for this polynomial. So that's the upper bound. And at the same time, we also want to do a lower bound. And for the lower bound, well, the process will be similar, but on the opposite way. So let me use this part again. Excuse me. So now I want to grab this part, and then I want to show you how to do the lower bound. Okay, so this is the upper bound. And then instead of greater, smaller or equal to, now, since we are doing the upper bound, we want to do what? We want to do a greater or equal to. And then how about in this time, instead of doing a plus b plus c, I do a mean abc multiplied by n. And mean abc multiplied by n squared, n, and the mean of the abc. Okay, so the trick is, well, I'm going to try to find the smallest value between a, b, and c. Okay, And then the a n square is guaranteed to be greater than the mean of between the ABC and multiplied by n square. So is that true? Okay. And then if it is, and then the same thing for the mean ABC multiplied by n and the mean ABC. Okay, so we are trying to find a lower value smaller than the a n squared plus b n and plus c. Okay, and then we are not finished yet, and our goal is, well, we are going to try to find a lower bound, and for this lower bound gn, well, gn c multiplied a constant c multiplied by gn is guaranteed to be smaller or equal to the fn. Okay, so we are trying to find a polynomial guaranteed to be smaller, right? So in this case, okay, we have already got this part, and then how about we do one more step? We want to get rid of this part. So we get rid of this part, so we only keep the smaller part. So what we only keep the first term, and then we get rid of the second two terms. So okay, so we are getting rid of something, so this one will be even smaller, right? Okay, and then if we want to have C as the mean of the ABC, and then we still have the n as the n0, what is going to happen? So for a n squared plus b n plus c, now I'm trying to do something smaller, so I'm trying to find the smallest value between a, b, and c, and then multiply by n squared, multiply by n, and then multiply by and just plus it again. Okay, and then after that, I drop the lower degree of polynomials, so I only keep this one, so it's even smaller. Okay, so if we stop here, and then we make the c. We make the c as the mean of the ABC, and then we let the n to be a 1. And what do we have? So now we are having a polynomial, and this polynomial is always lower than this original polynomial. So what is that? So let's take a definition. So we are trying to find the omega gn. And this omega gn this gn multiplied by c is always greater than 0 but smaller or equal to the fn for a given constant n greater than n0. Okay, so well, we are doing almost the same thing to big O n, but for the lower bound, big omega n, we are doing the lower bound instead of the upper bound. So for this part, since we have already got the constant, which is c, and then we have got the constant n0, so can we say for this polynomial, it is omega n squared. Okay, this is the constant c, and then this is the gn, and this part is the constant n0. Okay, so well, if we have a polynomial, well, and this polynomial is both big O gn, and it is also big omega gn, and then we say that is big theta gn. So if for a polynomial, it has an upper bound as the gn. It has a lower bound to be the gn as well. So it has to be, it is somewhere between those two. So that polynomial is the big omega gn. Okay, so for this part, you may find this is kind of different from what you have learned from another course, say data structure. You may have discussion about the time complexity, but the big O, big omega, and big theta, that is the term we are going to use in this course. Okay, so, and to give you some better idea, well, when we are trying to see the growth of the algorithms and we are not interested in the smaller values, we are trying to see the big picture when it gets larger and which is fast. Okay, well, one of the interesting is here. Well, O n cube versus 2 to the n cubed versus 2 to n, which is faster. So at the beginning, you may find that n cubed is faster. So how about we increase the scope? We increase the scope again, we increase the scope again. So what do you see? Well, you will see that when the value gets larger and larger, eventually, well, f at the 2 to n is going to be faster or grows faster than O n cubed, right? So, well, this is the reason we say we want to find a n0. For the n0, it is a start point when the one polynomial is greater than another one, or one polynomial is smaller than another one. So for all the smaller values on the left side, we don't care about that too much. We want to find an n0, and after this n0, one polynomial is either the upper bound of this one, or this polynomial is the lower bound of this one. So that is the reason we are discussing the n0. We don't want to come from 0. We want to start from a n0, so one polynomial is always the upper bound or a lower bound of the given polynomial. Okay, so well, here are a few more asymptotic notations. Like we have the big O and the big omega, and for the big O and the big omega, they are the upper bound and the lower bound. However, well, you can be smaller or equal to. So if a big O is exactly the same to the polynomial you are trying to evaluating, that's okay, because the big O is a smaller or equal to. So if they are exactly the same, they just together, that's okay. But if you're doing a small o, and small o is a strict upper bound, so it has to be at least a little bit higher than the polynomial you are evaluating. Okay, and for the small omega, it's the similar thing. So, well, usually we use the big O and big omega, and for some cases, you may see the small o and the small omega as well. Okay, so and then this is an exercise. So for a given t, so Tn is 5n cubed plus 3n, 5n cubed plus 3n and plus 10. So what is the big O? So for the big O, if we go here, okay, so if we come here, and then we can write a polynomial like bk nk. So k is the highest degree of polynomial, and then a lower degree of polynomials, and then we say it the highest degree of polynomial if it is k, and then this polynomial is big O n k, right? So if we just apply this, so for this part, if we say it is big O n cubed, is that correct? Yes, it is correct. And how about, well, if I want to give you some crazy case, say, okay, let me write this down. So big O in parentheses n cubed, that is definitely right. And then how about I do this? Big O n to 10, is that still right? Yes, it's right. And then because I'm using higher degree of polynomials, and then if the O n cubed is already a upper bound, and then how about O n 10, which is steeper, so it's also an upper bound, right? So how about I do 30? Yes, it is still an upper bound. Okay. So well, and then how about omega? So for the omega, and you may find it is omega O n cubed 2. Omega. Okay, let me copy omega first, and then it is omega n cubed. No problem. And then how about I try to be a little bit crazy? Omega 10, n to 10. Is that okay? No, because n to 10 is too steep to be a lower bound. So how about n squared? Is that okay? Because, well, if O n cubed is a lower bound, and then if we go even lower, O n squared, that's fine. And how about we go even lower? How about we just go omega n? Is that okay? Yes, that's still okay because we are going even lower, we are going even slower. But how about theta? Well, to be a theta, we have to use the same polynomial for both upper bound and lower bound. So what's in common? Well, for this polynomial, it is both O n cube and then omega n cube. So for that part, we can say, okay, it has to be theta n cube, okay? And theta n cube is the only correct answer in this case. So for the big O, we can go O n cube. We want to go higher degree of polynomial, that's fine. And then for big omega, it is omega O n squared. But if you want to go lower degree of polynomial, that's also fine. But for the big theta, the only correct answer is theta n cube. Okay. So well, I know it's kind of a lot of information, and well, if you have already got this book, you want to read the section 2.1 and 2.2, and this textbook explains that in a more theoretical way than I did. I try to make it understandable. And well, if you still struggle with this part, not a big deal, because in the next lecture, and I'm going to revisit part of the content I have covered today. Okay, well, and for the next part, and we will also start to learn how do we solve the recurrence. Oh, recurrence. That hurts, right? And for the recurrence, and coding recurrence is now the focus. And I'm assuming that you should be able to code recurrence. And we are going to do algorithm analysis on recurrence. Okay, and then for the homework 2 will be posted next class. So, well, I will try to spend some time to grade the homework 1 as well. Okay, so that's it for today, and I will see you next time. Bye.